Today we're going to take a little deeper dive in algebra world by looking at normal subgroups and factor groups. So let's get into it. So the first question we should address is, what do we mean by a normal subgroup? We understand what a subgroup is. We have a group G like this, and then you have some sort of group inside of that group that we call a subgroup H. But then we realized after we look at Lagrange's theorem that that's not actually an accurate picture using these circles and kind of these marbles floating around in space. We actually get something much cleaner where we have H is like one box or one little square of this group, and then we have these cosets that form the other boxes in this group. And the Lagrange's theorem is kind of a summary of that result, where we say that actually all the cosets are the same size. They partition the group so nothing falls into two cosets, and the left and right cosets are the same cardinality, and so therefore the order of my subgroup H has to divide the order of my group G. Now when I said left and right cosets, what I mean by that is that the left coset, like little AH, is taking everything in my subgroup and multiplying it on the left by element H. And my right coset is multiplying that in a different order, right? We multiply A on the right-hand side. So if I'm in an abelian setting, this doesn't really make a whole lot of sense to us why we have to distinguish left and right, because my operation is commutative. Okay. If I'm not in an abelian setting, though, these things may not be the same thing. So that's where normal subgroups come into play. So we say that N is a normal subgroup of G, and we write it like this, where we have kind of the sideways triangle N, triangle G, if your left and right cosets are always the same. Okay, now again, if we're in an abelian setting, this will always be the case. So for an abelian group, any subgroup will be a normal subgroup. So I think sometimes it's hard for us to imagine examples where this wouldn't be the case. So let's take a look at one. So my group setting now is S3. That is the symmetries on three elements. One way you can visualize S3 is by a triangle with labeled vertices, and all I'm doing is relabeling the vertices in some way. And with an equilateral triangle, this ends up being the symmetries of a triangle. Okay, so when I have this 1, I just mean that we don't do anything to the triangle. And if we do 1, 2, that means I flip vertices 1 and 2, or reorder vertices 1 and 2. These two things form a group, because if I flip vertices 1 and 2 and then flip them back again, I end up back with the identity. The identity element is the one here, where we just don't do anything to the vertices. They just stay the same. So this is a subgroup. Is it a normal subgroup? So it would be worth looking at left and right coset. I have a pretty clever example of a coset to look at, and that would be this one. So 1, 2, 3, H means I'm going to take 1, 2, 3 and compose it with the identity, and then I'm going to take 1, 2, 3 and compose it with 1, 2. 1, 2 being, remember that I flip vertices 1 and 2. So if I do this, composing with the identity, we don't do anything, and then we let 1 go to 2, 2 go to 3, 3 go to 1. With this second permutation, I first let 1 go to 2, and then 2 goes to 3, so I end up with 1 going to 3. And then I let 2 go to 1, which will go to 2. So 2 actually goes to itself. So I end up with just 1 and 3 flipping, and you can confirm that 3 does go to 1, because here first 3 goes to itself. Since we don't write it, that's what we mean. And then 3 gets mapped back to 1. So 3 ended up getting mapped to 1. All right, now let's look at the other coset, the right coset. So this time I'm taking the identity element and mapping it with 1, 2, 3. So I do 1, 2, 3 first, and then the identity. And then I'm going to do 1, 2, and then 1, 2, 3. So with the identity element, nothing special happens. So notice with my second element, 1 goes to 2. So we can track it here. 1 gets mapped to 2. And then 2 gets mapped back to 1. So 1 actually ends up mapping to itself. That's enough to show that these cosets are not the same, but we'll go ahead and finish this. 2 goes to 3. And then 3 goes to 1, which goes to 2. So all we end up with is that 2 and 3 trade places. And so notice these cosets are not the same thing. So here H is not normal. I'm sure we have a lot of colorful words we could use for not normal subgroup, but we'll just say it's not normal, okay? We'll play nice. Now the useful thing about a normal subgroup is that it leads us to this concept of called a factor group. And so what I mean by a factor group, and I write it like this typically. Here I mean, let's let N be a normal subgroup of G. And this is the set of cosets. Now, because these are normal subgroups, the left and right cosets are the same thing. So we don't really care from which direction we are considering. We usually consider the left cosets. Okay, so I think that picture that I had earlier of the rectangle might be useful here, because here I have my normal subgroup right there. And then after that I have these cosets. I have like AN, BN, CN, whatever. And you got to remember here, these A, B, C's, and F's and all this stuff are not in my normal subgroup, because if they were, so if I pick something in my normal subgroup and multiply it by something else in the subgroup, I would end up back in this box in the normal subgroup, right? So you got to think of this, where label this N, capital N. This is like a big box full of what? Full of the things in my normal subgroup. This box here, AN, is full of what kind of stuff? That's anything in my normal subgroup being multiplied by element A. So I have AN1, AN2, so on. That forms that box that I call AN. Now what I'm saying a factor group is actually a group where the elements in the group are these boxes, are these cosets. Right? So I said that this is a set of cosets here, denoted G over N, and this is in fact a group. We will show that it's a group, but I guess the first thing we need to figure out though is, what do we mean by plus or multiplication? I mean, how do you take two of these cosets and do something meaningful with them? And so we define, if I have AN and I want to multiply that by BN, all right, so I have two boxes and I'm multiplying those two boxes together. What's the result? The result would be the box labeled AB. So wherever AB ends up in my group, ABN or AN and BN multiply together to give me that coset, ABN. Now you might be wondering, does that actually work? That's a good question. We'll actually prove that it does work, and I'll show you some examples. But again, I want you to think about these factor groups as each element in the group is itself a box full of stuff. Okay, but we're only playing with the boxes themselves, not the elements inside the boxes. All right, so here's my first element, N, and then here's my next one, AN, and my next one, BN, and so on. So before I actually prove that this is a group, let me look at an example just to kind of talk about this a little further. So we're in S3 again. This time we take N, which is a subgroup, and actually it's a normal subgroup, being 1 the identity, and then 1, 2, 3, so that's 1 goes to 2, 2 goes to 3, 3 goes to 1, and then 1, 3, 2. So you can think of this as like a rotation in one direction and then a rotation in the other direction. These three things form a group. So first of all, S3 has 6 elements in it, and we already picked out 3 of them to be part of this subgroup. Okay, so if I'm looking at my cosets here, the first one I have is N, and then we would need to think, and since this is a normal subgroup, I don't have to worry about left or right, but I would need to figure out like what is this coset. And so what this means is I'm taking everything in my subgroup and multiplying it on the left hand side, or we're actually doing composition here, with 1, 2. So when I do this operation 3 times, I get the coset 1 goes to 2, and then I get 2, 3 swap, and then 1, 3 swap. So there's my coset. And notice that that actually gets the other elements as well. So if I did the calculation 1, 3 in, I would get the same coset. And same with 2, 3 in, I'd get the same coset. So my picture here is I have in my subgroup, and then I have that coset. There's S3. I knew that I would only have 2 cosets because Lagrange's theorem says that the number of cosets times the size of each coset is going to be the order of the group. Since I had 6 elements and the size of my subgroup was only 3. That only leaves 2 available cosets, right? Because 3 times 2 is 6. And what I'm saying here is that this actually forms a group because we could do some sort of Cayley table according to the operation that we talked about earlier. So if I multiply the identity by itself, and you got to remember that this is the coset 1n. So again, what we said was an times bn is the same as abn, right? So here if I have 1n times 1n, I just end up with 1n. If I have 1n times 12n, I end up with 12n. And we could keep doing this. Now, does this actually make sense what I mean? So what this coset would be is that I'm multiplying 1, 1, 2, and then n like that. And if I did that, just like we did up here, I would end up with this same thing. So we do end up with a Cayley table of 4 elements, and our operation does make sense, though it can be a little confusing at first. But this does form a group on 4 I said 4 elements. It's a group on 2 elements, right? Okay, let's prove this now. We say we're going to let n be a normal subgroup of G. Then the set of cosets form a group that we denote G over n. This is our factor group of n, and it has a cardinality of the index Gn. And just to remind ourselves, this is the index, which is the number of cosets. So of course, if it forms a group then of the set of cosets, then how many things are in it? Well, just the number of cosets. That is what the index is. Okay, so let me just give a quick sketch of what this proof requires. So first, we need to make sure, and this is kind of the hardest part, make sure that this operation actually makes sense to us, that this actually does something. The mathematical way of saying that is it's well defined. And then secondly, we need to show if it's associative. That will be easy. We have an identity element. That's easy as well. And inverse elements. And that's actually easy as well. Okay, so 1 is the only hard part here. And let me show you how to do that. So we're going to take 2 things, or 2 cosets to be equivalent. So we'll say, let's let an equal cn and bn equal dn. All right, so we have 2 pairs of equivalent objects. And what I want to make sure is that, like, if I multiply a and b, do I get the same thing as if I multiply c and d? Okay, so if I take the box an, multiply it by the box bn, is that the same as the box cn times the box dn? Okay, all right, so then what I could say then is that a equals c times n1, and b equals d times n2 for some n1, n2 in my subgroup, because a is in the cn box and b is in the dn box. Okay, so then if I multiply ab, getting the box ab, that's the same thing as saying cn1 dn2 capital N, right? So this is that box's label. But notice here I'm multiplying n2 times all the stuff in capital N. So that's the same thing as cn1 dn, because n2 times all the stuff in n is still that same box n. Now, because this is a normal subgroup, I'm allowed to do this trick. cn1 capital N d. Why is that? Because left and right cosets are the same. And now I can absorb that n1 as well. So I end up with cnd, which gives me cdn. So my operation is actually well defined in this case. All right, now the last few things we can go through pretty quickly. We know that this operation will be associative because we're just doing actually multiplication in our group. Our group is associative as well. The identity element is en, which is just your subgroup, is your identity element. And for coset an, whatever your inverse coset is, a inverse n, whatever your inverse element of a is, a inverse n is an's inverse. And that's because we're just borrowing the operation here. an times a inverse n is going to be a inverse n, which is just your identity element. So there we have it. We do indeed have a group. Okay, now that all that's away, let's look at another example. Okay, I also want to point out with this previous example before we move on that if I look at this Cayley table and I relabel n as 0 and 2n as 1, I actually get the same Cayley table I would have for Z2. And so we actually know, since this is a group of two elements, my factor group that I have here is what we say isomorphic to Z2. So operation with these symmetry groups, this factor group with the symmetry groups, is actually the same as doing Z2 arithmetic. All right, let's look at another example. So this time we're going to let n be 4z, and by 4z we mean the multiples of 4. And this is a normal subgroup of the integers. We know that's normal because this is an abelian group. The integers are abelian. So it makes sense to talk about then this factor group, z cross or z over 4z. Okay, now you have to remember what this means. This means the cosets that we get where we let 4z be the subgroup, what kind of cosets do we get? We're playing with those cosets. Okay, so I need to start thinking about what these cosets look like, I guess. So 4z, again, are the multiples of 4. So I got to figure out what the other cosets look like. So I could, for example, say 1 plus 4z. And so I end up with 1, and then plus or minus 4 plus 1, and so on. Okay, so maybe that's one of these. I could also do 2 plus 4z, and I could do 3 plus 4z. And then if I do 4 plus 4z, I end up back to the beginning. So actually, my cosets are 2 plus 4z and 3 plus 4z, and maybe we can call that one 0 plus 4z, the original. All right, so now we have a 4-element group, and maybe it looks very familiar to us. This actually is isomorphic to Z4. In fact, when we talked about Z4 in the beginning, what we said was Z4 is made up of the equivalence classes on the integers with mod 4 arithmetic, meaning that if two things fall in the same boxes because they're congruent mod 4, that's exactly what we're pointing out here with these cosets. Two things are in the same coset if they're congruent mod 4, because it's a multiple of 4 plus whatever that is. So multiple of 4 plus 3. So all of those guys are equivalent to 3 mod 4. So I think we can make a pretty universal statement here that if I have the integers divided by some sort of multiple n of z, that's actually just zn. That's actually just the integers with mod n arithmetic and getting those equivalence classes. Okay, so that in a nutshell is factor groups. Factor groups are very important theoretically going forward. They help us do a lot of cool things. They're a lot of fun to look at. If you have questions on this, please let me know. You can do it. You just got to keep working hard. And I look forward to seeing you next time. Thanks for watching.